This lecture video is meant to introduce you to the ideas of energy and power that are associated with having electric current, right? So the big background idea is still, we're studying the current, but the notions of energy and power are very important in situations that have electric current. So let's talk about a circuit. So I've got this battery, and I've got the battery, the language that you use is you say, this battery is powering this device. And the device can be any number of things, really. So you could consider the device being simply a resistor. And in the case of resistor, you can use it as an electric heater or a toaster, right? Somehow, when you use various types of resistors, when you power the resistor with a battery, right, you get this electric current set up in the circuit, and the battery is energy, right? It's not an infinite amount of energy. So as you use your battery to power this resistor, your battery's energy is diminishing, right? It's getting less and less. And meanwhile, your resistor is sending the energy out as heat, right? So this is an energy conversion from energy stored up in the battery as electric potential energy into thermal energy, right? Heating energy. And even in the case of very, very warm things, you'll also see a lot of light coming away from this, especially if it glows red hot or white hot, right? It takes energy to create light. And that energy, the origin of it was somehow it was stored up in the battery, right? Once you have used all the energy of the battery and it doesn't have any more available as electric potential energy, your device doesn't work anymore, right? So this is the conservation of energy. Okay, so our system is that we can study, right? With electric current, we can power or energize a device. But the device doesn't need to just be a resistor. It can also be a little motor, or you can recharge other batteries, right? Recharge a battery. That's a possible device. Okay, so here is a little bit closer up of a picture of the device. Right, so the device in the circuit is here. I'm just looking at the device sort of by itself, but imagining that the rest of the circuit still exists. What happens is, right, if you look at the way the battery is oriented, you've got the long plate, the positive plate, right? This is the high potential side of the battery. And the other side of the battery is the lower potential side of the battery. And what a battery does is it maintains the potential difference, right? It maintains a specific value is the idea. So a AA battery is a 1.5 volt battery, or you could maintain 6 volts or 12 volts or 9 volts, right? So there's various voltages that you can maintain. But the point is that's the battery's job, is to maintain a potential difference. But you know that potential difference is associated with electric field, right? So roughly speaking, it's the integral of some electric field, right? Dotted with displacements along the length over which the potential varies, or over which the potential changes, or over which the potential has a difference, right? So the battery maintains the right-hand side of itself, right, which is the positive side. The high, it maintains it as the high value of potential. So over this conductor, right, this perfect ideal conductor, the potential is the same value all the way, because the electric field is 0 all the way. So there is no change in potential along the wire. So that potential is extended all the way to the right-hand side of the device. and the lower side of the battery is extended its potential value all the way to the left-hand side of the device. And so there is this potential difference across this device, and there is an electric field in there. So that's the electric field in the device. And if the device is a conductive medium, that is, it's got a resistivity, but whatever its area and length are, and whatever the potential difference is, a current can flow. The current flows in the direction from high to low, and the current flows in the direction of the electric field. And I'm talking in terms of the conventional current. But if you follow the way this current flows, so it's going to flow towards the left in the device. Actually, let me take that. Let's make it black. So it flows towards the left in the device. It's going to flow around the corner this way and around the corner this way. It's going to flow this way across the battery, right? Because it's flowing in a cycle. It's a circuit. And this current is flowing in this cycling sense everywhere at the same time with the same value, right? So this is the current I in my circuit. So the current I through the device follows the electric field set up by our battery. Now our battery is a very different kind of thing. So I'm going to caution you that what goes on inside the battery is special. But you do know that the battery has an electric field because there's going to be an electric field here because it also points from high to low, right? So there's an electric field in there. Just like here, the electric field is pointing from high to low. You notice that the battery electric field points from right to left because the high side's on the right. The device's electric field points from right to left because the high side's on the right. But the problem is the electric field, not the electric field, the current in the circuit is still flowing towards the right. It flows backwards. So the current flows backwards against the electric field in the battery. The reason it flows backwards is this question mark. It's the way the battery works, which is there's a lot of science for batteries. But the point is the current is going to flow opposite to the electric field that the battery sets up. So when you have this kind of situation that the electric charges flow in the opposite direction of the electric field, this represents a loss of energy, right? In a sense, there's a negative amount of work being done. But up here, you might say that this is something of a gain in energy. When the charges flow in the direction of the electric field, we kind of gain energy in a sense. So there's a loss of energy through the battery when the current flows through it, if it flows opposite to the battery's electric field. But up here, we say this is a gain in energy in a sense. Okay. Batteries lose energy when the current flows opposite its electric field, right? Which is what I'm drawing up here. But batteries gain energy when the current flows in the same direction as its electric field. This is what's meant by being able to recharge a battery. Now, it depends actually on the design, on the question mark aspects of a battery, on whether or not it's rechargeable. Some batteries, they're not meant to be rechargeable. You may be able to sort of restore. I don't know, 0.1% of its energy by running it backwards, if it's not necessarily rechargeable. But rechargeable batteries are designed so that every time you recharge them, you can stick back in an appreciable amount of energy. Right. This is why lithium-ion battery technology, if you are a professional in this engineering field, you're going to make a crazy amount of money, right? Because this essentially is one of the issues in the world right now. It's easy to have a tank where you store up gasoline, right? It's just essentially a watertight container, right? And you can run a gas engine from it. But a battery is a very, very special place to store up energy. And not only do you need to be able to store up energy in this battery once, but you need to be able to cycle the battery. That is, use the battery, right? Use all the energy from a battery and then fill it back up hundreds of thousands of times before anybody wants to buy a car that's going to be powered by one of those batteries. So there is so much engineering in this problem, right, of lithium-ion rechargeable batteries, and this is money, right? Okay, so you should, I don't know, go get a job in this world. All right, so batteries can gain energy as well in the recharging sense. But anyways, so let's study the device because it's a little bit easier to study it. So here's the device. Let's imagine, right? So let me draw it again. So here's the device, and here are the little metal contacts. That's the low side and the high side. All right, so let's talk about energy first. If charge amount Q, right, so electric current is because of a bunch of little charges, right? And they're going to flow this way, right? I'm talking about the conventional current sense. And I can imagine an amount of charge in there that adds up to Q. And if this charge amount crosses the device, then there is an energy associated with this equal to Q times the potential difference, right? The potential difference is the voltage of the high conductor minus the voltage of the low conductor. So the amount of energy is just the amount of charge times delta V. If I want to know the power is the time derivative of this energy. And the time derivative of the energy, right? So we're imagining delta V. The battery provides a steady voltage that does not change in time. So the time derivative skips it, right? It doesn't notice that delta V changes in time because it doesn't. So the only thing that changes in time is the amount of charge moving across. And what you can do is then you say that the power is equal to delta V times dq by dt. And this right here is the rate at which charge crosses the device. It's I, right? That's the current. And so typically people write P is IV, but really it's a potential difference that it's crossing, not a particular value of voltage. But yeah, so it gets shorthanded to this expression. So this, for a resistor, for example, it could be power dissipated as heat, right? So there's a certain number of joules per coulomb. An example is, let's say that you have, a device. Let's say it's 200 ohms. And let's say that I'm going to put so let's say the high conductor side is at 10 volts, and the low conductor side is at negative, no, let's just easy, let's put it at 0. So 10 volts minus 0 volts is a potential difference of 10 volts. And so if I have 10 volts across 200 ohms, I wonder what the current is. So the current, right, I go I times R is V. This is Ohm's law. So I can solve for the current. It's V over R. The voltage is 10. The resistance is 200, right? So 10 over 200 is 1 over 20. So this is 1 over 20, and it's a current, and I used SI units, volts and ohms, so I get SI unit amp, 1 over 20 amps. So now I have a current, and I still know the voltage. So the power dissipated equals, right, it's I times V, so I is 1 over 20 amps, and V is 10 volts. So it's 1 over 2, right, 0.5 volts per amp. But let's look at this unit. So it's 1 over 2. A volt is a joule per coulomb, and the amp is a coulomb per second. So I have, for units, I'm dividing a fraction by another fraction. And the way you divide two fractions is you take the top fraction and you just put it down, and you take the lower fraction and multiply by its inverse, like this, right? Did I do this right? Oh gosh, no, I didn't do this right. So the current is not 1 over 20 amps on the bottom. The current is amps on the top. So I'm going to put the amps on the top, and I don't have to divide. Oops, I'm so sorry. So let me fix everything. So it's really volts times amps. So the volt is a joule per coulomb, and the amp, actually let me fix this. So the volt is a joule per coulomb, and the amp is a coulomb per second. So this is 1/2, so the coulombs cancel. I get joules per second. And a joule per second, that is the definition of the watt. Right? So I just calculated the power dissipated. So if this was, this is referred to as Joule heating, named after Joule. But the point is when you have the current flowing through this resistance, what's happening is the resistor warms up. It gets hot, right? The temperature can rise and things like that. Okay, so this right here is also how you would calculate the power lost by a battery. If the current I flows through a battery and that battery's voltage is V, then I times V is the power lost by that battery, is the idea. All right. Let me tell you one other sort of useful fact real quick. So for resistors, the power is I times V, right? Actually, this is just true for anything, right? If you know the voltage across it and the current through it, then I times V is the power, sort of like, you could say it's the power transformed, or depending on the context, right? Up here, I was saying this was considered power dissipated, right? So that's a conversion somehow of electric potential energy into thermal energy. But for resistors, the relationship between the voltage, the current, and the resistance is given by Ohm's law. So for resistors, you can just replace the voltage with current times resistance. So it's I times R, or I squared R. This is a really convenient form for the power equation. Another thing you can do actually is solve for the current instead. So I is V over R. And so you can also write the power equation. So this is one form. You can, so instead of replacing the V, replace the I, and you get V squared over R. Yeah, so these are heat dissipation rates from resistors. Another one that's kind of cute is imagine the device being a motor. So here, let's say this is the device. I'm going to turn the circuit sideways. And what we're imagining is over here, so this is the battery, and this is our device, but our device is a motor. And it's got like a spool of string tied to the end of a mass, right? And what you can do is use your battery to increase the gravitational potential energy of this mass, like raise the mass, right? So you will use energy at some rate of power, right? And be able to lift, right? That is, provide gravitational potential energy, or at least a force over a distance to increase the gravitational potential energy. And the faster the current that flows, the faster your mass will rise, right? Yeah, but this is an energy conversion that probably also involves some heat dissipation. So not only are you accomplishing the task of lifting the object, right, doing that mechanical work, you're also fighting internal frictions and resistances. So you're also heating up the world. And the energy of the battery is going to do those two things. So you would say if you generated a lot of heat from your motor, you would say that's not a very efficient motor, right? Efficient motors don't generate very much heat. The energy from the battery goes mostly to doing the work, right? You'd say that was efficient.